Hi, I'm Dr. J, and this is a video about Bayesian statistics. This video comes in a playlist all about statistical inference where we talk about both Bayesian and non-Bayesian approaches. If you're interested, down below there's a PDF version of these slides. Alright, so let me just give you a brief outline of what's going to happen, ideally in this video if we can all contain it all in one, but certainly in this slide set. So we're going to talk about Bayesian parameter estimation as an approach to inference where you condition on what is known. And you describe your belief about the unknown using the language of probability. We're going to introduce some terminology like turning a prior into a posterior. Talk about posterior expectations and credible intervals. And throughout the video, we're going to be talking through the binomial example where we have an unknown probability of success. Alright, so now I want to introduce my concept of what a Bayesian statistician is. And we're going to do it through some mathematical notation, so I need to introduce some terms. We're going to let Y be some data from an experiment that individual will be conducting. And we're going to have capital K here not be a random variable like it is normally, or not even an event or a set. But instead, capital K is going to represent everything that is known about the world, according to that individual, aside from this experiment that they just performed. And then we're going to have theta represent everything that's uncertain to them. They might know something about theta, but they don't know everything, right? And that's why they're running the experiment. So then a Bayesian statistician for me is a statistician or individual who makes decisions based on the probability distribution of things we don't know, conditional on the things that we do. And so as notation, we could write this as P theta given Y and K. Right? So we're making decisions based on this distribution for theta given Y, the data from the experiment, and K, everything else that we know. Alright, so let's see how we can put this into practice. I should remind you, yes, that K is typically dropped from the notation. So if you read the literature, right, they will typically not have this K put in there, but really it's there implicitly. Okay. Alright, so a Bayesian statistician gets its name from Bayes' rule. We talked about Bayes' rule earlier. Hopefully there'll be a link up here talking about Bayes' rule. And we introduced this definition for Bayes' rule right here in terms of events. So the AI's and the B's in this equation are all events. And the key aspect of the Bayes' rule is that you can flip the conditioning. You can turn it around. So you'll see on the left side of the equal sign, you have probability of AI given B. But on the right hand, you have all of these B's given AI's, right? One in the numerator, and then in the second equation, a whole bunch of them, possibly a countably infinite number of them in the denominator. All right, so we're going to take this idea, and we're not going to prove it at all, but we're going to apply the same idea typically to densities, or sometimes probability mass functions. So here is the same looking equation where we have now put theta and y. So remember, on the left side of the conditioning, left side of the equal sign, is what we're trying to determine as a Bayesian statistician. We're trying to find the distribution of the things we don't know, given the things that we do. And now Bayes' rule is going to allow us to flip the conditioning. So we had on the left side p theta given y. On the right side, we have p y given theta times p theta, all divided by py. And the appealing aspect of this equation is that it's going to give us a density or perhaps a mass function on the left-hand side of the equation. In a previous video, we talked about the likelihood, and perhaps if you watched that video, you might have been thinking that the likelihood looks an awful lot like a probability density function. Unfortunately, it wasn't, but Bayes' rule here tells us how to convert that likelihood. Right? Remember, the likelihood was related to py given theta. It takes that likelihood and it turns it into a probability density function, so you can use all of that probability language that we've determined before. Now I'm going to go one step further in this equation, and I'm going to write out that denominator, py, as an integral. So py given theta times p theta d theta. Right? So I just am trying to point out here that to get that denominator, we're really integrating over theta over this p theta. Alright. So that integral plays the role of the sum up here when we talked about this in the context of events. Let's talk about applying Bayes' rule to parameter estimation. And when we do that, you will see why I chose to use the notation that I used. So now y is going to be data, say from an experiment, and theta now is going to represent an unknown parameter, possibly a parameter vector, right? And we're going to apply Bayes' rule here, so we just have p theta given y is equal to py given theta times p theta divided by py. And now, when we apply this to parameter estimation, what we're typically going to call these terms, on the left-hand side, we have the posterior, or typically the posterior density. On the right side, we have the prior, that's p theta, the prior density, or prior mass function, depending. We have py given theta. That is what I'm going to refer to as the model or data model. Sometimes people refer to this as the likelihood. And previously, we defined this as being equal to the likelihood, so you could do that, no problem. And then we divide here by py, and that's called the prior predictive distribution. We're going to leave that aside for a while now, but we're going to come back to it when we talk about model comparison or Bayesian hypothesis testing, where in that context, we're going to need something called the marginal likelihood, which is just the prior predictive distribution evaluated at the data that we've observed. So that's actually going to be a number. Okay, so here we have our posterior and our prior, right? And the idea of this Bayesian parameter estimation is to use the data through the likelihood or model to update your prior into your posterior. So you start with your prior, you incorporate the data through that model, and then you get your posterior. Right? So, as a reminder, at the beginning of the slides, we talked about the interpretation of a Bayesian approach to inference is through a belief. That's how we interpret probability. And so really, this parameter estimation is telling you mathematically how to take your prior belief and turn it into your posterior belief. That is to turn p theta into p theta given y. Okay, so here now we have two different distributions for the parameter, right, theta. We have the prior and the posterior, and the key to distinguishing between these two is to determine if you're conditioning on the data y. So here's a quick summary of where we're going and where we've been. So that first line, we typically have a density. So we have p theta, that's the prior. Then we have p theta given y, that's the posterior, that's been updated through the data y. From that density, we can calculate an expectation. We're going to write the expectation in the prior as just e theta, and the expectation in the posterior as e theta given y. We might be interested in a posterior variance. Well, that's going to be variance of theta. A prior variance is variance of theta. The posterior variance is variance of theta given y. Right? We might be interested in probabilities. Right? And when we condition on y, we're talking about the posterior. Otherwise, we're talking about the prior. Okay, so let's just get more concrete here. So that was sort of the general outline of how we do parameter estimation in a Bayesian sense. Here we're going to apply it specifically to the binomial model. Right? We talked about the binomial model in an earlier slide. Hopefully there'll be a card up there. And the binomial model, remember, is just a model for the number of successes out of n attempts. Right? So it's an integer from 0 up to n. It has a probability mass function right here, given a value theta. That's a probability of success. And so now what we have to do in order to do Bayesian parameter estimation is to assume a prior distribution for that unknown probability of success. Well, probabilities have to be numbers between 0 and 1, so we want some kind of distribution on 0, 1. And it seems reasonable, in the absence of any specific information about that probability of success, to assume that we have sort of no information about that probability of success, and therefore we're going to assume the prior is uniform on the values 0 to 1. That means that every probability is equally likely within that unit interval, within the interval 0 to 1. Right? So if we do that, we have something called the uniform distribution on 0, 1. I'll probably change this in the slides actually to be uniform, because we've talked about uniform distribution. We talked about it up here in a previous video. This is just another way to write that uniform distribution using an indicator function. We have talked about the indicator function previously, but as a reminder, an indicator function is 1 if the statement in between the parentheses is true, and it's 0 otherwise. So a very trivial function, right? That's either just 0 or 1. In this case, this probability density function for theta is just 0 outside of the interval 0, 1, and between 0, 1, it's uniformly at 1. Alright, so if you use this prior with that likelihood, it turns out that you can derive the posterior distribution, the posterior density, and it turns out that the posterior, this theta given y, it's probably the first time we've seen that written in that format, right? So on the left side, there's a random variable theta, given known values on the right side, in this case, y. Okay, so the distribution for theta given y is a beta distribution with parameters 1 plus y and 1 plus n minus y. Now, if you've been following along with these Stat 587 videos, you probably have not heard of a beta distribution. And so let's just take a moment to talk about this beta distribution. So the beta distribution defines a distribution for a probability. That is, numbers on the interval 0, 1. So its support is the interval 0, 1. The probability density function right here looks a little bit complicated. First off, the indicator just tells you it needs to be between 0 and 1. On the left side, you can see this theta raised to a power and 1 minus theta raised to a power. So between the support and that notation, or that mathematics, theta raised to a power, 1 minus theta raised to a power, that's how you recognize a beta distribution. In the denominator, you have this beta AB. That's something called the beta function. So the beta function here is defined as the product and ratio of gamma functions. The gamma functions are defined by this integral right here. But for our purposes, we don't need to know this. Right? We're going to be using, say, the software R to determine how to do calculations using the beta distribution. And so this is just for completeness, but you don't need to know it. Okay, so a couple of properties of this beta distribution. So first off, it has two parameters, A and B. Those are often typically both referred to as shape parameters, and so there's not really much distinguishing between the two. In a moment, you'll see that A is related to the number of successes, and B is related to the number of failures. Okay, at least in the context of a binomial model. So a couple of the properties here is that the expectation for this beta distribution is A divided by A plus B. The variance is a little more complicated. It's A times B divided by the quantity A plus B squared times A plus B plus 1. And then finally, the beta distribution with both parameters equal to 1 is actually the exact same distribution as a uniform 0-1 distribution. Alright, so let's get back to, this is a slide, about looking at some particular beta densities. So among the facets here, notice that we're always looking at numbers between 0, 1 on the x-axis. And along the facets, we've changed the values for A and B. So we've changed the values for B across those columns and the values for A down the rows. And now here, I just want to show you sort of the flexibility, but when A and B are small, you get something that looks like a U-shaped curve, right? And depending on what the values for A and B, that U-shaped curve might change. When A and B are relatively large, what you get is a peaked distribution, like in the bottom right-hand corner down here, right? And so that's typically going to be the scenario that we're working in when we use this as a model for binomial observations. Okay, so let's get a concrete example here. We have a binomial experiment where we have, say, 100 sensors, and 2 of those sensors have a sensitivity that's below some predetermined threshold. Okay, and suppose that we call y that number that are below the threshold, and we assume that the observations are independent. Therefore, we have a binomial model with n equals 100 and theta, this unknown probability of success. And now, perhaps we have no other information, and so we're just going to assume a uniform distribution for theta. That uniform, remember, is the same as a beta 1, 1. Hopefully using this beta 1, 1 here will remind you that the posterior is also a beta distribution. That posterior is specifically a beta with the first parameter being 3 and the second parameter being 99. So now notice here how that first parameter is the number of successes. In this case, the sensor being below the threshold is a success. But that first parameter there is 1 plus y, so the number of successes plus 1. The second parameter is n minus y. Well, that's the number of failures, so add 1 to that. And so we can think about that first parameter here for the beta as being related to the number of successes, and the second parameter as being related to the number of failures. Okay. Here's the posterior density for that particular beta distribution. So this is for a beta 399. First, notice the x-axis, right? Remember that a beta distribution has a support 0 to 1. But I've cut off the figure here at 0.1 because there's very little density above 0.1. Okay? And so here we can see this beta distribution has most of the support there right around must be around 0.02, right? Which was the actual value of the number of successes that we observed, or the number of sensors that were below the threshold. Okay, so that's the answer as far as the Bayesian is concerned. That's the posterior density, that's your objective. Now, oftentimes it's inconvenient to hand somebody that whole density, and so we might want to summarize it in a more succinct format. So one way, if you're only given one number, is to provide an estimator of that posterior, or a point estimate from that posterior. And what we'll typically use in this class is to use the posterior expectation. So I'm going to refer to that, for the purpose of these videos in this class, as the Bayes estimator. If you're watching this from somewhere else, I realize that Bayes estimators are more complex than that, and they involve a utility. But for simplicity, for these videos, we're going to call that posterior expectation the Bayes estimator. Okay? For a beta distribution, that's going to be 1 plus y divided by this quantity, but there's some simplification you can do, so you have 1 plus y divided by 2 plus n. In the context of this particular example, we find that that Bayes estimator is actually close to 0.03. And that brings up a question here. If you went back to a previous video where we talked about the MLE for binomial distribution, we noted that the MLE was just y divided by n. And we also noted that the MLE is unbiased. So it turns out that the Bayes estimator is actually biased, or generally at least, but it's still consistent. And as a reminder, for an estimator to be consistent, it just means that the probability of being too far away from the truth decreases as the sample size increases. So an expectation is fine, but an expectation doesn't really capture that whole posterior. So what we might want to do instead is to provide something called a credible interval. So here we're going to introduce the generic notation for a 100 1 minus a% credible interval. If this is your first time seeing any kind of credible intervals or confidence intervals, then think about a as being sort of an error rate. And typically a is pretty small. A common value for a will be 0.05. And if a is 0.05, then we're going to construct a 95% credible interval. So a credible interval has two values because it forms an interval. So we have a value that's the lower endpoint and a value that's the upper endpoint. And the key with this credible interval is that what is required is that if we integrate the posterior density from L up to U, that is across those endpoints, then that probability must be 1 minus A. Okay? Now, there are many different ways to construct this credible interval, so one way that specifically defines what L and U must be is to have an equal tail credible interval. So the equal tail basically just says, I want to make sure that half of my error is on the left tail and half of my error is on the right tail. And so this notation right here just says, look, if you integrate up to L, then that should be half the error, or A over 2. And if you integrate from U up to infinity, then that should have half the error, which is again A over 2. So that provides a specific value for L and U. Using some R code here and the Q beta function, we can find the endpoints of that interval. In this case, rounded to 3 significant digits, we have 0.006 and 0.70. 0.07. There we go. As a visual demonstration of this equal tail credible interval, we have this picture. So the red area in this picture has a probability, or has an area of 0.95. That is, the probability is 0.95 of being between those two locations on the x-axis. And it's constructed so that half of the error is on either side. So that means those two white areas under the curve both have an area of 0.025. All right, so let's just summarize what we talked about in the context of Bayesian parameter estimation and specifically within this binomial model. So first off, if you're going to do a Bayesian parameter estimation, you have to specify a model for your data. You have to specify a prior for the parameter. You have to then use those two to derive the posterior. And as a reminder, what this posterior is doing is updating your prior belief about that parameter into your posterior belief about that parameter. Finally, we might want to summarize that posterior by calculating some quantities of interest, for example, a posterior expectation or a credible interval, perhaps an equal tail credible interval. Now, specifically for the binomial model, this is the one we're probably going to use pretty often in this course, is to say, all right, we have binomial observations, and we can assume a prior distribution. Now, here I chose an arbitrary A-B beta distribution, right? So the two parameters are just A and B, not necessarily 1, 1, although going forward we will likely use 1, 1. And if we use this beta distribution, then the posterior distribution is another beta, but we've replaced those 1s with A and B. So we have A plus Y and B plus N minus Y. I just want to remind you that a beta 1, 1 is equivalent in distribution to a uniform 0, 1 distribution. That is, in some sense, providing no information about the parameter theta that's of interest. The last thing I have here is a summary for some R code about how you might want to do calculations in this binomial model. Alright, so that wraps up this video. In the next video, or sequence of videos, we'll start talking more about Bayesian and non-Bayesian approaches to statistical inference. Hope to catch you there.